All right, so we hope to have Hack 1 out by the end of the day sometime, along with comments. And it looks pretty good overall on the grades for Hack 1. Remember that Hack 2 is pushed back a day. It's due on Tuesday right? It's due on Tuesday at midnight instead of the usual Monday at midnight. Same thing with your reading. Reading 3.0 is due on Monday or Tuesday evening. Excuse me. All right. So to continue where we left off last time, we've got if-else-if conditions. Right. All right. Let's lower our voice, okay? All right, so if we've got a condition here that's either true or false, an if statement, and sorry for the folks over here again, try to crane your neck, or you can go ahead and follow along on YouTube. And for anybody else, we've got a YouTube and Piazza here. All right, so an if condition, if it's true, then the entire code block is going to execute. Alternative, or it won't execute at all, right? It'll just continue with normal control flow after the if statement. With an if-else condition, you still only have one condition, but then you have two statements. Either statement A will execute or statement B will execute. We call those things mutually exclusive, all right? So if the condition above evaluates to true, then statement A is executed. If it evaluates to false, false, statement B executes. But only one and exactly one of these statements will execute. These are mutually exclusive. They exclude each other. So if A happens, B doesn't happen. If B happens, A doesn't happen. They exclude each other. Exactly one will execute. You can extend and abstract this, I guess, whatever you want to call it, to an if-else-if statement. So you can extend this to as many conditions as you want. I'll keep it simple by giving you two conditions here in this basic syntax. Condition 1 and condition 2, right? So if condition 1 holds, if it's true, then statement A gets executed. Otherwise, if it's false, it moves on and checks the next condition. All right, is condition 2 true? If so, then it executes statement B. If not, if it's false, then it continues on and on and on. You can have as many of these statements as you want. Else if, else if, else if. And then at the end, you can have your else statement. If none of these things are true, then if all else fails, you just do the else. Right? And you can do those as many as you want. You can have as many else if, I'll write it like this, else if statements as you like, along with as many conditions. All conditions are mutually exclusive again. Right? Exactly one and only one will execute. Right? And for that reason, order matters. Right? The first one that is true is the one that will get executed. Right? For that reason, if you're going to structure a large if-else-if statement like this, the most specific conditions need to go first. The most general last. So if you've got a hierarchy of these things, right, then it follows that hierarchy. Very, very specific, less specific, less specific, more general, more general, more general, until you get down to the else, which is absolutely the most general, because if none of those conditions happens, then the else statement takes over and executes. Just like the if condition, an if-else-if condition is the same thing as an if condition with an empty else statement, right? It's optional. Likewise, you could make this one optional. You don't need to do that, right? You can go ahead and have a statement like this. If this condition, then execute this. Otherwise, if this condition, then execute this. Otherwise, don't do either one. Right? And you could make statement C empty and do nothing, right? You could just simply take this out and have an empty line of code. Don't do that. That's cruft, right? If you have dead code like that that does nothing, remove it. That's bad style. Okay? And of course, you can have as many conditions as you want. Right? So observe the style, right? Opening curly brackets are on the same line as the conditional, right? Or the condition. each closing curly bracket is at the same indentation level as the if statement, or at the other ones, right? It's all aligned. We've got a nice vertical alignment here of if, closing, 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 right? And everything inside of a statement, each block is indented. And again, if you want to, you can use 2 spaces, 3 spaces, 4 spaces, tabs, whatever you want to use, as long as you are being consistent about it. Don't use 4 spaces in one indentation and then 5 spaces in the next one. It should all be the same. Okay? Well, now that we've got the basic if-else-if syntax. Oh, sorry. Go ahead. Oh, yeah. Sorry. Go ahead. I didn't see you. You won't have to, as long as you're consistent about it. This is old school GNU style right here, right? And if you want to go that way, great. I don't like it personally because it makes it way too vertically white-spaced, I guess, and spaced out. And that means that you're always, large code blocks, you're scrolling up and down all the time, right? I like to compactify things and focus. But as long as you're consistent about it, go ahead. In fact, remember that we have on Canvas that online C formatter, right? Beautifier, formatter, whatever. We can probably take this and reformat it. Okay, it's only got one format here. But the one that we provide on Canvas has a couple of choices of style guides to follow. There's a Google style guide, there's a GNU style guide, and it'll reformat it to conform to those style guides. Right? Otherwise, if you just want to use, say, I don't know, what was that utility at the command line to fix everything? A style, artistic style, right? CSE, E. A style demo. There we go. And close it, reopen it, and there we go. Nicely indented now. Right? Don't get in the habit of writing garbage code and then relying on a tool after, right? At the beginning, yeah, go ahead and use that so that you can see what good code looks like. But ultimately, what you're going to want to do is you're going to want to write nice looking code, good stylistic code as you go along. Right? You want to get into that good habit. There are good habits, there are bad habits. Right? Any others? No? All right, so conditionals. Right? Or sorry, conditions. Numerical comparisons. So you can compare 2 literal values, or you can compare integer, variable values, etc., using the, say, strictly less than operator. That's on your QWERTY keyboard. That should be pretty straightforward. You can use the less than or equal to. Now, if we were in math, it would look something like this. But do you see that nicely styled math on your QWERTY keyboard? No, there's a way to get it through Unicode, I'm sure. But go back 50 years to the old when they were doing this and they only had the nice QWERTY keyboard. You have to approximate it. Less than or equal to. And it is written as less than or equal to as we would say it. It's not written equal to or less than. No, right? Nobody says it like that. Nobody writes it like that. That looks like a right arrow. And in some languages, that has a meaning of mapping this thing to that thing, but not in C. Right? So less than or equal to, this is less than or equal to. And you need to use both of those characters. Likewise, you have a strictly greater than and then a greater than or equal to, right? But you also have equality operators. You have equals equals, right? And not equals. Now, why do we have to use 2 equal signs for the equality testing? Yeah, it's already the single one is already used for an assignment operator, right? It already has a meaning, so we can't have 2 different meanings for the same thing, at least in most cases. And then we also don't have this nice, not equal sign, right? Right? We don't have that on our QWERTY keyboard where we could just write a sign and then slash it through, right? We don't have that, so the approximation there for inequality is an exclamation point and then the equal sign. Okay? All right. All comparisons operate on two operands, a left-hand side and a right-hand side. Right? They could be either one could be a variable, a literal, that is just a hard-coded value, or an expression. But both must be numerical. Numerical. There we go. They can't be anything else. And I'll show you what I mean by that here in a second when we look at this demonstration. All right, so we've got this example from last time where we've got if A is equal to 10, then the Huskers will win for some reason this weekend, right? Otherwise, don't make any bets, right? Let's go ahead and generalize that to the actual scores here, right? So int, Husker score. Why did I use an integer here? In football, can you have a half a point? Are there any sports where you could have a half a point? Other than like Olympic sports, you get an average of 10.2 or something, or perfect tens or 9.8 or something like that, right? Nope. So it's got to be an integer. If something is a whole number, you use an integer. If something is not a whole number, you use a double. Right? Those are the correct the types that you should be using. And then what is it, North Dakota? Score, right? And if the Husker score is less than the North Dakota score, there we go, printf. That's really unfortunate. What happens? Not until October. Money, buyout goes down, right? All right, so what happens? Huskers lose, unfortunately. Right? Otherwise, else if the North Dakota score is greater than Husker score, hopefully I'm spelling everything correctly. If I'm not, yell at me. Printf. Now this is nice. Right? This is expected too. The money line is like 22.5, right? So that's the spread. So, but the spread was like 12.5 last week. So who knows, right? But Huskers will win. Right? There we go. Oh, sorry. There we go. There. If the North Dakota score is less than the Husker score, then the Huskers win. Now, is that the only two possibilities? They could tie temporarily, because we do not allow ties in football, right? So, tie, what do? We go to overtime. There we go. And so each one of these, I'm comparing a variable value to another variable value, right? A variable value to another variable value. Right? I could also do, say, an entire expression. Let's go with doubles here. Double A, B, and C, right? And if B times B minus 4 times A times C is all less than 0, then what should we not do that we were doing on Wednesday or whatever it was? We should not take the square root of that, because then it would be a irrational, or it would be a complex number, right? Not irrational, but complex number. Printf cannot compute a root, ... There we go. And so maybe later on we'll incorporate that into our quadratic program that we were building before, right? And do something else instead. Otherwise, you can go ahead and print it, compute it. That was an entire expression on one hand side. On the other side, the right-hand side, it was a literal. It was a hard-coded value, in this case, 0. In the original examples that we were looking at on Wednesday, we were hard-coding those to 5 and 10 and 20. Those are called literals. These are variables, and these are entire expressions. Right? I'll go ahead and, by the way, this is a good question. What will actually get printed right now? Ignore that. GCC demo. What will actually get printed here? Will the Huskers win, lose, or go into overtime? Yeah, I don't know. We haven't. Do they have any values? Remember, what are the default values in C? Could be 0, right? It could be that dead beef stuff. It could be garbage. We don't know. I'm willing to bet, in fact, I'm willing to bet more on this answer than the actual game outcome of that they will in fact be 0. And so we'll go tie and we'll go to overtime. Right? Excellent. But again, that is a quirk of that particular compiler of that particular system. The C standard does not define any default values at all for uninitialized variables. That's why you should always initialize them. Right? Okay. So, style tip. Right? You can, but probably shouldn't, do the following. So if I've got int a equals 10 or something, it equals ... I'm not going to write real code there. It's initialized to whatever. I shouldn't write this. If 10 is equal to a, then printf a is 10. Why shouldn't I do that stylistically? Well, first of all, it looks wrong. And the reason that it looks wrong is try to read that. If 10 is equal to a, then do this stuff, right? Versus the original one that we did on Wednesday, where we had if a is equal to 10. Which one of those is read correctly or sounds natural when you read it out aloud? Hopefully the first one, right? And so if you're comparing a variable to a literal, probably want to put that variable first, right? Because that's how people are going to read your code. They're going to read it in their head in plain old English. And if it doesn't sound right in plain old English, then that means that they're going to have a pause and and then have to think about it. You want to write code that people don't have to think about, that they immediately see that and immediately understand what it's doing. Yeah?
Can you do something like if 9 is less than x is less than 50, if you want to do in between those numbers?
Hold that thought. That's a pitfall. We'll do something like that in here in a second, right? You can, but shouldn't, do the following. Or you can, but should never. I'm going to stress this one. Should never do the following. So int a, there we go. If a is equal to a, printf a is a. Yay. Right? Why should you never do that? Is a going to be equal to itself? True, yeah. If it's always true, it's something called a tautology, right? If you've ever had any logic classes, you'll hear about that. Don't worry about it. It's something that's always true. Why would you write that? If you just want to print a as a, then go ahead and print a as a. Don't surround it in a condition that's always true, right? A condition, or if 10 is equal to 20, right? Printf, something is wrong. Right? Is 10 ever going to be equal to 20? No, that's something that's false, always false. That's called a contradiction. And if you're going to write that, that's dead code. That code will never execute ever, right? Because of the logic of the hard-coded values that you put in there. So don't write stuff like that, right? Write stuff that makes sense, okay? Some other, general negation operator, right? Any statement can be negated, that is flipped, true to false, false to true, using the general negation operator. Just like not equals, it's going to be a exclamation point. Sorry, I don't know why this, because I never ended the code. There we go. There we go. And why are you ended there? Ended there. Okay, there we go. Any statement can be negated using the exclamation point. For example, I could write, it is not the case that A is strictly less than B. Right? Now, I put parentheses there because parentheses become important. Just like algebra. Think about an algebraic expression here. Right? I'm going to go into LaTeX mode here. Let's say negative A plus B, the same as negative A plus B. Right? Are those two expressions the same? Definitely not. Logic-wise, it's also the same case. If you've got a negation, you want it on the entire expression, you need to put parentheses there. Otherwise, you're only negating whatever A is. And we'll talk about what that means here in a second when you negate a variable. Okay? But otherwise, you can do that. But what's a better way? What is a better way of writing this? It is not the case that A is strictly less than B. What's the flip side of that? What's the opposite statement of that? Right. A is greater than or equal to B. Let me code that. There we go. Is a better way to write it. Right. Why? Because it's simpler. Right? Now you can put parentheses around that still, and you're really not saving in terms of the number of characters, but reading it is where you're saving time, right? Reading it and understanding it. Nobody says it is not the case that A is strictly greater than B, right? Nobody, or less than B. Nobody says it like that. They say A is greater than or equal to B, right? And so write it like that, right? If it's clunky to say out loud, it's probably clunky to code. Think of a better way of doing it, right? And in general, you want to KISS. Keep it stupid simple, right?
Or
Simple, or, well, yeah, that's the original, right? But I don't want to call it. We don't want to call ourselves stupid. We want to just stupid simple, right? Just keep it simple, right? So, keep it simple. If you've got simpler code is always generally better code. Now you can get down to simpler code that becomes unreadable, and that's unreasonable. You've got to find the Goldilocks zone. Why do we call it the Goldilocks zone? 3 bears, right? The porridge is too hot. That porridge is too cold. That porridge is just right, right? So that code is too complex. That code is too simple. That code is just right, right? Somewhere in between there, right? Questions? No? All right. Well, what does it mean if I do write A, not A? Then that means that we have a Boolean variable. Right? By default, C does not have Boolean variables. If it did, what a Boolean variable is, a Boolean variable is a variable that holds the value, and I'm putting it in quotes here because this is not real code, true or false. Right? Okay? So the way that we do this in C, numbers are used instead. 0 is false. Anything else is true. Right? In other words, 1 is true. And that's usually what people use. Right? But also, 42 is true. 10.4 is true. -5 is true. Right? And it's because it's got to be consistent. If you negate 0, you get something that's not 0. And so what's true? If you negate false, you get true, right? You have to consider all possible values. Right? So let's go ahead and take a look at what that looks like over here. A Boolean variable, since we don't have Boolean variables, we have to use an integer, say. Right? And I'll go ahead and name this isStudent. Right? And I can't set it equal to true. I can't set it equal to false because those keywords are not built into standard C. Instead, I need to set it to false, or I can set it equal to 42. That's true, right? Don't be weird, right? I'm going to show you what happens when you're weird like this, right? So, if you are a student, you get free football tickets. I don't know. Free football tickets. You don't. At least I don't think you do. Yet, if the sellout is in danger, then you'll be getting some free tickets to preserve it. Question? Oh? Okay. All right, so if they're a student, if you use numbers, you get in the habit of asking, well, is it equal to true? Well, 1 is my placeholder for true here, right? 42 is true, so are they a student? Yes. Will they end up getting their free football tickets? No, right? Why? Because we were being really pedantic about it. We were only saying, if it's equal to 1, 1 isn't the only true value, right? 42 is also true. 10.4 is true. So to write this as better code, you don't use the equality here. You just use the variable itself. That will evaluate to true or false automatically for you. In fact, it's even easier to read. If is student. If they are a student, then they get free football tickets. And now if it's 42, if it's 1, if it's 10.5, it doesn't matter, it will work. Right? If it's false, in fact, the only time that it's going to not work, you're not going to get your tickets, is if you are not a student. Right? So that's the much better way of doing it. Now let's go ahead and find an even better way of doing it. Right? However, like I said, you don't have these things in C. However, you can use a library. That library is called the STD Bool library. What do you think it stands for? The Standard Boolean Library, right? It defines a bool variable type. It defines the keywords true and false. False. There we go. Am I already bringing it in? Nope, I'm not bringing it in, so I'm going to show you that in fact it is a library. If I want to set bool is student to be true, it isn't going to compile, hopefully. Yep, what are you talking about? I don't know what true is. I'm just regular old C where we've got numbers instead. Right? So let's go ahead and bring in that library now to take care of our work for us, stdbool.h. And now, it's, stdbool.h. I saved it, right? There we go. Gee. What? Oh, thank you. That would make it difficult. There we go. And now it works, but I've actually got a Boolean variable here. Some programming languages use the full Boolean, but this is defined as bool. Right? In fact, what you can do is you can click on that library and see how it does it. What does it do? It just defines bool, and later on it defines it to be an integer. True is what? 1. False is 0. Now true is 42, and I break all your code. Thankfully, it won't let me do that. I can't save that. Don't save. I can't go changing the standard libraries. I mean, you could, but then you'd have to recompile everything from scratch. Right? And I would break all that terrible code that was assuming that 1 is always the true value. Right? That's a good way to enter a malicious C contest. Right? But there's an example using the Boolean library. Let's see. There we go. All right. Let's see. More complex logical expressions, right? So far we've only done numerical comparisons. What if you want to search for a range of values as you asked before? You can combine logical statements using connectives, such as the logical and logical or, right? And I'm putting, again, those in quotes because they're not actually keywords used in this language. Some programming languages, like Python, actually use and or, the English words and or. C-style syntax does not. Instead, the logical and operator is true if both sides, right, that is its operands, are true. Is true only if both sides of its operands are true. The syntax here is something that makes sense. Ampersand, ampersand. What is the actual English meaning of the ampersand? And, right? A law firm, Jones and Bartlett, right? How do they do it fancy? They put a ampersand after it, right? But it's 2 ampersands, not 1 ampersand. If you do 1 ampersand, it will compile and it'll run. It has a completely different meaning. Well, not a completely different meaning, but it's a bitwise AND operation, right? We're not going to be doing bitwise operations here. It's called bit twiddling, so don't worry about it. Just understand you need 2 of them, right? And, right? Example. A is strictly greater than 10 and B is less than 5. Right? I'm combining both of those. If you feel more comfortable about it, go ahead and add parentheses if you want, but it's not necessary. Right? It wasn't necessary in that particular case. In general, I personally do it because I don't remember what the order of operations is, and I don't want to have to always go back to a reference manual to remember that, Oh yeah, the greater than and the less than, those are operated on before the logical or operator, right? Forget that, right? Don't have to worry about it. Just go ahead and add parentheses so make it absolutely clear and so that you don't have to remember the order of operations of stuff. Sure, of course, remember PEMDAS because that was driven into your head through grade school, right? But logical operators, forget about it. Just remember, put parentheses and not have to worry about that garbage. Right? All right. If so, let's test. Right. Let me go ahead and take this over to our coding environment, and let's go ahead and create int a b, and put this into an if statement. I'll put it right here. There we go. And there we go. And you tell me, is it going to print true or is it going to print false? Now I have uninitialized values here, so it's probably going to be 0, 0. I've got too many parentheses there. There we go. All right, but let's go ahead and give it some values. Is equal to 10, and b is equal to, say, 10. 10 and 10. Let's walk through this and understand, which one is it going to predict it. A is strictly greater than 10. Is that true or false?
No.
False. So do we even need to look at the second one, by the way?
Nope.
It's only true if both of them are true, but let's look at the second one. Right? B is less than 5. Is that true? Is 10 less than 5? Nope. Neither one of these is true. So predict what it's going to print. False. Excellent. Let me change this so that it is greater than 100. 100 is certainly greater than 10, right? Now the first one is true. But I didn't change the second one. That's still false. So true and false is going to end up being what? False. They both have to be true. Only when I go down below 5 here, say 4, right, and above 10, now what's it going to print? 100 is strictly greater than 10. 4 is strictly less than 5. So they're both true. The and, because, oops. I need to actually compile it. There we go. There, true. Right. The bang there, we call it in Unix programming. We call that the bang because it's an exclamation point, right? So there's a slang term that we just call it the bang, right? And then bang G means that you are executing the previous command here, if you've seen me doing that. So that I don't have to type out GCC blah, 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 right? If you get really adept at using the command line, you will be, it'll end up like being one of those stupid hacker movies where somebody is just, pounding the keyboard and they're getting, a bunch of code, right? It won't be that dramatic, but you will be able to code around somebody who doesn't use the command line all day long. You'll be able to run circles around them. So just get used to it, right? Because it is so useful. Right? All right, that's I should have called that demonstration. Right? If either the first or the second or both end up being false, the entire expression is false. Only if both sides are true is the expression true. Its companion is the logical OR operator. Is true if at least one of its sides is true. Right? One of its operands, excuse me. The syntax here is, well, there's no OR on your keyboard. Eventually, when you do take a discrete math course or you take a logic course, you might see V and wedge. That's the OR and that's the AND, right? Of course, those are not on your QWERTY keyboard, so we have to use something else. The bars, or the vertical bars, or the pipes, right? Whatever you want to call them. And just like the ampersand, it's two of them. If you only have one, it's a different meaning. It's a bitwise OR operation. So you need two. Okay? Example would be from above, but replacing replacing the AND with the OR. Right? Again, it is true if if the second, or the first is true. It is true if the second is true. It is true if both are true. It is only false when both are false. Right? So let's test this out over here in our coding environment. Let me go back to the original values here. There we go, 10 and 5. And I will go ahead and put the pipe there. Right? What's this going to print? False. Why?
It's not looking at equals or greater than both.
Right.
Equal.
This one is 10 is strictly greater than 10? False. 5 is strictly less than 5? False. So they're both false. But the second that I make either one true, the first one is now true, but the second one is false. Now it becomes true. Undo that. Make the second one true, but the first one false. True. Make them both true. True. Right? And we've got true. Right? There we go. Excellent. So, now let's talk about pitfalls to finish out the day. Pitfalls. Right? You cannot, in fact, I'm going to emphasize that. 3 stars here. Cannot, all right, use numerical comparison operators on anything other than numbers. Right? Okay, so what do I mean by that? Let me go ahead and try to write some code here. In fact, I'll just hard code these values. So is apple equal to apple? I don't know. Unfortunately, I think that this is probably going to print true, but for other reasons. Yep, true. So it seems to work, right? Well, which comes first, apples or oranges? Do apples come before oranges? Oranges. And what do I mean by that even? Like the intuitive notion here would be what? Dictionary order, right? So A comes before O, right? Seems to work. Unless I swap them around. Apple. Oranges come before apple. That should be false, right? But it ends up being true. Right? In other words, it's unreliable to use these numerical comparison operators on things that are, say, strings. Right? When we talk about strings, we'll talk about the proper way of doing this, using a function, a string comparator function. What's going on here is that C is saying, oh, okay, well, those two things are, the apples and oranges, those are two things that are stored in memory. So does one come before the other? That's simply asking, does this thing come in memory before this thing down here, right? What does that have to do with the actual apples and oranges? Nothing, right? It's just that it got loaded up in memory before this one got loaded up in memory first, right? And I did it in order here because I think that the compiler will end up loading this in memory first because it's on the left, and then it'll load this thing up in the memory next because it's on the right. It just goes in order, right? And that's all that it's comparing. All that it's comparing is, are they equal? No, but are they not equal? That'll end up being true too, right? So don't do that. You can't do that, okay? You cannot use numerical comparison operators on anything other than numbers. It will end up comparing memory addresses instead of the contents of strings. More later. When we eventually get to strings, we'll look at the way of doing that better. Okay? Here's another pitfall. Bad ranges, we'll say. All right. So consider the following piece of code. This goes back to your question. What happens if I want to check for a range? I want to make sure that A falls between 0 and 10. What's this going to print if A is equal to 5? That's right smack dab in the middle, right? It should print out, I'll change this to true. All right. So what's it going to output? 5 is right between 0 and 10, right? True. Okay. Let's test some corner cases. Corner cases are, say, at the edge of each one of these ranges. 0. What's it going to say? True. All right. Looks like it's working for me here. Right? True. All right. Ship it. Commit it to my GitHub repo and push it out. I'm done. Did I do enough testing? No. This is exactly why we ask you to write 3 test cases before you even start on your hacks, right? So that you have a nice expected or input, expected output. You run it on your program, and if you get something different, you made a mistake. Maybe you made a mistake in your original test case design. Maybe you made a mistake in your code. But in any case, you've got something to fix, right? That's how the grader works. We give it an input. We have an expected output. Does that match your output? If so, great, it passes, right? Testing. In order to have confidence in your testing, though, you need to have a lot of testing. What didn't I test here? Things outside the range. -10. What should it output? False, or nothing in this case, since I don't have an else statement. Still outputs true. What happens if I go above that range? 100. It will also output true. We need to understand why here. Let's walk through it left to right. First of all, it evaluates this. Is 0 less than or equal to 100?
Yes.
Yes. What is yes? What is true? 1. Is 1 less than or equal to 10?
True.
True. That's why it printed true. Undo, undo. -10. Is -10 or is 0 less than or equal to -10? No. False. What is false? 0. Is 0 less than or equal to 10? Yup. That's why it ends up being true. Don't do that. Write better code. What's a better way of writing this? Using a logical AND. Right? But I'm going to show you a preview of what you're going to want to use to see problems like this. When I compiled this, did GCC care? Apparently not, right? Again, GCC is going to say, all right, you want to do that? Go ahead, all right? Unless we tell it, you know what? I want you to give me some warnings. W stands for warnings. ALL stands for all of them. Tell me about everything that's possibly wrong here. It's called a static analyzer, a linter. A, comparison of constant 10 with Boolean expression, that's always true. What? Comparisons like x is less than or equal to y, x less than or equal to z, do not have their mathematical meaning. You're not in math, you're in coding, right? You're in computer science here. That has a different meaning here, right? And therefore, there's something wrong here. It's just a warning, though. You want to do that? Go ahead, right? That's your business, right? But it is giving you a warning about this now. The proper way of doing this, right? And again, the above always evaluates to true, the reasons I gave. Instead, use what? Right? If I need to split those two conditions up. If 0 is less than or equal to a, and a is less than or equal to 10, then printf true. End the line. Right? By splitting those up, that's proper logic there, right? And that will work. Some programming languages won't even let you do this thing up here. All right, some programming languages will count this as a compiler error. You might even be able to you might even be able to force C to become like really strict and not compile this, but maybe not, because that would still conform to the that conforms to the standard, right? That's how they wrote it. Here's another pitfall. Tell me about that code. Do you see the problem? Squint really hard. Yeah. One equal sign, right? Now, if you had bad white space, maybe it's even harder to see that, or maybe it's easier now. I don't know, right? But if you had a really compact monotype font because you were using really cool Google fonts or something like that, it might not become apparent that that's only one equal sign there, right? Use standard fonts, right? Don't get fancy, right? Let's go ahead and put that down here. All right, fine. Indent. There we go. A is equal to 5, and then if it's equal to 10, we output true. Is A equal to 10? Nope. But, oh, okay, ignore that. Don't warn me about it. There we go. It, in fact, is true. What's happening here? Because it's only one equal sign, it's an assignment operator. Assign the value of 10 to A. Well, what's the value of 10? True. Right? And that ends up printing out true. Right? Don't do that. And again, if you use a proper linter here, it'll warn you about that. Hey, that if statement, along with the parentheses around it, suggests that you're probably trying to do something else. You're doing an assignment. Are you sure you meant to do that? Re-examine that code. Right? So, don't do that either. Right? So the mistake was using a single equal sign instead of the proper double equal sign, which is the equality operator. Here's our last pitfall for the day, and then we'll talk about that thing called a linter. Consider the following code. What's wrong with it? Stare, squint really hard. Right? I can zoom in if you want. Something does not look right. Yeah. Semicolon right there. So what's it going to do? Here I will make it so that int a is equal to 5. There we go. Is it going to print out a is equal to 10 or not? There we go. Let's find out. A is 10. It's not. I fixed my mistake, right? I've got two equal signs there. But the mistake here is the semicolon. Reformat your code and read it. If A is equal to 10, do what? Nothing. Right? Nothing semicolon. Remember that a semicolon is like a period in English. If you write a sentence with no letters or words in it and put a period there, did you say anything? No, that's nothing. And it's also not proper English, but it's also weird code, right? You wouldn't do this in code. Right? And again, if you use it, the compiler properly, let me go ahead and recompile that, but with the nice wall flag, the WAL flag. It catches that too. It says, wait a second, the if clause does not guard. Note this statement, but the latter is misleadingly indented as if it were guarded. Guarded means that it's bound to that thing, right? That this thing right here is bound to this if statement, but it's not, right? If A is equal to 10, do nothing. Then continue with the rest of the program. Well, the rest of the program prints 10, right? Or prints A as 10. So be careful, right? The if statement executes an empty executable statement, right? Statement because of the extra semicolon. Right? So how can you solve all these problems? By using what's called a linter, right? So code may be syntactically correct, right? It may compile, but it's not right. Just like your clothes, they might be clean, but they're not necessarily right. Right, now put on a suit, right? It's a nice clean suit, or a shirt, like a dark shirt, say, right? That just came out of the laundry. It's clean because you put it through the laundry, you put it through the dryer. But what does it have on it, potentially? What comes out of the dryer? Lint. Right? It's clean, but we've got lint that we need to take care of, right? Garbage. Stuff that probably doesn't belong there. So in real life, what do we do with our lint? We've got a lint brush. It's a sticky thing that you roll over it, lint roller or whatever, and it takes off all the lint. You have something similar with code. If you write with the WAL flag, it's a linter. It goes through and finds those little pieces of code that probably should not be there. It's not necessarily wrong because your code is still clean, just like your clothes are still clean, but that lint should not be there. Let's take those out. Warnings. Right? We'll pick it up there on Wednesday because remember, Monday it is Labor Day. There is no lecture there.